Good morning, everyone. Let's start this last morning session of the conference, Homological Symmetry, with Melissa Liu from Columbia University, and she will speak about Coulomb correspondence about person in Abelian linear sigma nodes. Melissa.
Thank you for the introduction. I wish to thank the organizers for the invitation. It is my great honor to speak at this conference. Today, the title of my talk is Higgs-Coulomb correspondence and wall crossing in abelian gauge linear signal models. So there's a warning that the Coulomb range in my talk will be different from the Coulomb range in Sergei Gukov's talk and Nick Krasov's talk. It's not hyperkähler. This is based on joint work with my colleague, Konstantin Aleshkin. So we would like to dedicate this work to the memory of Professor Bunsi Kim. As you will see, our work relies heavily on his work, and he has done most of the hard work. Yeah, so first I will introduce the geometry of gauge linear signal models. So the Higgs range in this talk will be defined by virtual counts of Landau-Ginzburg quasimaps, which we will introduce. We will first introduce it for any genus, but today we will focus on genus 0 and abelian case. We'll introduce Landau-Ginzburg loop spaces and define I functions in the GLSM setting. And we will define central charge on a B-type D brane, which depends only on the bracket B, which is the K-theory class. So the Coulomb range for the same K-theory class, we associate a hemisphere partition function, which is a Mellin-Barnes integral, and it is the equivariant perturbation of the hemisphere partition function defined by Horry and Romo. Our version of Higgs-Coulomb correspondence is a relationship between the hemisphere partition function in the Coulomb range and the central charge in the Higgs range. And finally, I will talk about wall crossing in the Kähler moduli. So the input data of a gauge linear signal model is a 5-tuple V, G, C star R, W, and zeta, where V is just a complex vector space of certain dimension M. And the gauge group G is a subgroup of GLV. It acts linearly and faithfully on this V. And there is another C star subgroup of the general linear group. And so these two subgroups commute, and their intersection is finite. So it must be cyclic, generated by some element J of finite order R. So for later convenience, let C1 to Cm be the weights of the C star action on this vector space V. So the R charges is defined to be 2Cj over R, where R is the order of the intersection of G and C star R. So that's V, G, and C star R. So W is the superpotential. It is a polynomial function in x1 to xm. It is invariant under the action of the gauge group G and is quasi-homogeneous of degree R with respect to the C star R action. Finally, zeta is the stability condition. It's a G character. It's a G character which defines a G linearization on V. So we assume zeta is chosen such that the semi-stable locus is the same as the stable locus. And the consequences, if we consider GIT quotient stack, it is a smooth Stirling-Mumford stack. The coarse moduli space is GIT quotient. The coarse moduli space is projective over its affinization. And then there's now the C star R action before the quotient descends to C. So C star omega is quotient of C star R by this finite subgroup J. It doesn't act on V, but it acts on the quotient. And with respect to the C star omega, the superpotential, so little w is the superpotential defined on the affinization, and also it pulls back to the GIT quotient and smooths the Landau-Ginzburg stack. So with respect to C star omega, the superpotential is of weight 1. So we say the gauge linear single model is abelian if the gauge group G is abelian. In most of this talk, G is not only abelian, but actually just a torus. And in this case, so we have a short exact sequence of abelian group. So G is we may assume by inner automorphism, we may assume that this G is contained in the diagonal big torus in GLM plus kappas. And the quotient torus is n-dimensional. So here the weight of the G action is given by m plus kappa characters. Okay, so yesterday we have this talk of the quantum toric stack. So this is just the toric Landau-Ginzburg, classical toric Landau-Ginzburg stack. So the stack GIT quotient stack is a smooth toric Landau-Ginzburg stack. And so the coarse moduli space is a semi-projective simplicial toric variety. And we can also view it as a symplectic quotient. Then the stability condition zeta can be in R kappa, like can be real. And then the space of stability condition R is like, so the chambers in stability conditions are the top dimensional cones of the secondary fan. Okay, the first example is the quintic example. So V is C6 with coordinate. With coordinate x1 to x5 and P. The gauge group is just C star, so there's only one Kähler parameter. The gauge group acts by weights 1, 1, 1, 1, 1 minus 5, and C star R acts by weight only acts on P. The superpotential is P times the Fermat polynomial, Fermat quintic polynomial in 5 variables. So in this case, the Clavial, so when zeta is greater than 0, it's a Clavial or geometric phase. In this case, the toric orbifold is actually a toric variety, which is the total space of the canonical line bundle P4, and the critical point is the Fermat quintics inside the 0 section P4. And in this phase, we will GLSM invariants are Gromov-Witten invariants of the 0 locus. So in general, like when the critical locus is smooth and we can define Gromov-Witten invariants, then GLSM invariance should be equal to Gromov-Witten invariance. But when the critical locus is like too singular, one cannot define Gromov-Witten invariance, and this GLSM invariance should be viewed as the replacement of Gromov-Witten invariance. It should be viewed as virtual curve virtual counts of curve in the critical locus. So when zeta is less than 0, this is a Landau-Ginzburg phase. In this case, So the stability condition says the last coordinate P cannot be 0, so one can use the Caesar action to scale it to 1, and we get this orbifold, a fine orbifold C5 mod mu5. The critical locus is like supported in the origin, and in this case, GLSM invariants are FJRW invariants of the Fermat quintic polynomial in 5 variables. But in the general setup, the GLSM, like in the general phases, they don't correspond to Gromov-Witten invariants of FJRW invariants. So let's continue with this example. So in 2008, Kyoto and Ran established a version of Landau-Ginzburg Clavial correspondence for quintic threefold. So Landau-Ginzburg Clavial correspondence says the Gromov-Witten invariants of the quintic Clavial threefold should correspond to FJRW invariant of this W5 mu5. So their proof can be summarized in 2 steps. So first, so we will see later why this is called epsilon wall crossing. So this was so in the Clavial phase, there's a Giventhal style mirror theorem proved by Giventhal and Lian-Liu-Yao in 1996-7, which says the J function, which is a generating function of genus 0 Gromov-Witten invariance of the quintic Clavial threefold, is in terms of I function under the mirror map. And the I function is in terms of some very explicit hypergeometric series. And then Kyoto and Ram prove a similar theorem in the Landau-Ginzburg phase. So then J minus is a generating function of genus 0 FJRW invariance of this Fermat quintic polynomial in 5 variables. And in both phases, there are functions of 1 variable and takes values in a 4-dimensional complex symplectic space. So the second I will call zeta wall crossing, because we see like this is a stability condition from zeta greater than 0 to zeta less than 0, and I plus and I minus are related by analytic continuation and a complex linear symplectic isomorphism between these 2 4-dimensional complex symplectic spaces. So the question is now the general GLSM as invariance, as we will see in the next section, it was only defined very recently in 2020. So the question is, we can now study this epsilon wall crossing and zeta wall crossing for more general GLSM. But then let's just remind ourselves what happens when, in the case like GLSM without superpotential. That means you just have a vector space with the action G and the stability condition. And that is orbifold quasimap theory. So orbifold quasimap theory. So there's an epsilon stable quasimaps to this GIT quotient of vector space by a linear reductive group G. And they introduced the notion of epsilon stable quasi-stable maps. And this allows them to define J function, which depends on epsilon. Essentially, what happens when epsilon goes to 0 plus, one gets the I function. As epsilon goes to plus infinity, one gets a J function. And then they prove quasimap wall crossing. So that's why. So then this quasi-map walk crossing is proof at the level of cycles, and will imply this given style mirror theorems relating I and J. So that's why the first step can also be viewed as thanks to this work, can be interpreted as epsilon walk crossing. And then, but now this V is actually a general, so G is not necessarily abelian. So this in a particular will imply mirror theorem of smooth story Dillingman stack by Close-Cody Irritanianson. So now this orbital, the epsilon walk crossing orbital quasimap theory in all genera, in full generality has been proved by Yang Zhou. So at the level of virtual cycles. And so now the general GLSM theory has defined, it's expected his proof is generalizable to GLSM. And then this will imply given style mirror theorems for all GLSM in all phases. So I think at least I think Joe can prove it if he wants to, I believe. And also I think Mark Shoemaker might be working on it. So in any case, I think there are more than one mathematicians working on this. And so now let's, and actually this is already proved in the GLSM for associated to complete intersection in weighted projective spaces. So I think we will not worry about the epsilon walk crossing because this is much more general in all genera, and it will in particular in genus 0 will imply this kind of mirror theorem in the form I is equal to J under mirror transform. So today we will focus on I functions and zeta walk crossing, and we will focus on abelian GLSMs. Okay, so first, so the Higgs branch is about virtual counts of so GLSM invariants are defined by virtual counts of Landau-Ginzburg quasimaps. So this is rely on the foundational work of Van Jarvis-Run and Favreau-Kim. And so Van Jarvis-Run defined the invariants in the so-called narrow sector, or more generally with compact type insertion. And so for the general GLSM, it was only defined full generality by Favreau-Kim in 2020, while virtual factorization. And they also proved that their GLSM invariants satisfy the axiom of co-FT. So this generalized the previous construction on applying Landau-Ginzburg models and convex hybrid models. So I want to briefly describe, so just give a very rough idea, not very precise. So then we start with a general GLSM. G is now not necessarily abelian. And then G and C star R generate a subgroup in GLV, and we have this short exact sequence. So the quotient of gamma by G is this C star omega. So this map is a character which we call chi. So now Landau-Ginzburg quasi-map. So is a GL pointed degree beta epsilon stable Landau-Ginzburg quasi-map to this. Yeah, because this is a 5-tuple, so I write this as this mass graph X underline. And so it consists of 4 tuple. So the first ingredient is a GLL pointed nodal orbit curve. So it can have orbifold point at mark points and at nodes. At nodes, there's some balance condition, and we want to trivialize the germ at mark points. And P is a principal bundle, gamma bundle. So recall that gamma is generated by this gauge group G and C star R. So it's a principal gamma bundle. So that's P. And rho is a trivialization. So rho, actually, you recall that we have this gamma to C star omega character chi. This gives us associate line bundle associated to this gamma character. And rho is an isomorphism between this line bundle and log canonical of C. So yeah, that's probably why it's called C star omega. And finally, U is a section of the vector bundle associated to the representation gamma. So this four condition is, yeah, basically defines a map to the smooth arting stack V quotient by gamma. So there's a from V. So yeah, so there's map V to a point and induces the map to V gamma, which is this principal bundle. And and then the character from gamma to C star omega induces this map from D gamma to BC. Yeah, so we require this diagram commutes. So this diagram, the lower diagram commutes is like the third condition. And the upper half of diagram is also equal to a F tilde equivariant map from the principal bundle to V, or equivalently a section U of the associated vector bundle. Yeah, so we can think that this will in particular give us a map from your curve to V quotient by gamma. And so the final condition is so there's a so the first line is the pre-stable condition that the base locus, which is like the part goes to the unstable locus, is only finite and disjoint from mark points and nodes. In particular, the mark point cannot go to the unstable part, so we will have evaluation map into the inertia stack of the GIT quotient stack. And the epsilon condition is yeah, so I'll just say there are epsilon stability condition without saying this precisely, because today we will actually focus on the epsilon 0 plus. So yeah, so that's the space and this moduli space. So we form this moduli space. So it depends on the given GLSM input data, and there's a genus and number of mark points and degree, and also this epsilon stability condition. So and then we have evaluation map to the inertia stack of this smooth orbifold, and the inertia stack is is decomposed into finitely many components labeled by a finite subset B theta. Oh, so then we can just further decompose it because each mark point can just map to one of the connected components. So we can further decompose this moduli space into like open and closed substack by specify like the connected component. So now we fix the GL beta and this V1 to VL connected components of the inertia stack. And so then the evaluation at the ith mark point goes to some connected component labeled by VI. And then like curly Zi is the critical locus of the superpotential. And also, like, this is a moduli space, so this both at Z in X, we require actually the corresponding map actually is contained in the like critical locus. So Fan-Java's run proof that, so this X is usually a non-proper separated Deligne-Mumford stack of finite type equipped with a perfect obstruction theory. If we also fix this V1 up to VL, then there's a fixed virtual dimension. If we don't fix them, then they might be different for different VIs.
Can I ask a question?
Yes.
The W here, where does it appear on this slide?
Oh yeah, yeah, very good. So because this definition does not depend on W, right? So there are 5 tuples. So this definition only depends on V and G and C star R. So C star and G together generate gamma. And the stability condition for the GIT is zeta, right? So this definition, and epsilon is something. So epsilon I haven't stated, but the moduli space actually doesn't depend on W.
So that's additional data.
Yeah, so the thing is the thing is it's like the virtual construction of the virtual cycle will depend on W. And so it will in some, yeah, you want it to, the virtual cycle to be supported in Z. Oh, sorry?
The LG quasi-maps.
Yes.
Don't involve the superpotential.
It doesn't, the moduli space doesn't depend on the superpotential. Yes. Okay, that's very, so yeah, so the construct, so basically so if the critical locus, yeah, of the superpotential is proper in our target GIT quotient stack, then they prove that Z is a proper Deligne-Mumford stack. So first, so this is a brief description of Farrell-Kim's construction. So they show that there exists a smooth Deligne-Mumford stack of finite type, a vector bundle over U such that X is in, so X is our moduli of Landau-Ginzburg maps. So embedded U as a zero locus of this vector bundle. And so you see that we already have a perfect obstruction theory, and yeah, and X is so X has a perfect obstruction theory. X is also a separated Deligne-Mumford stack. So we can define this Baron-Fantacchi virtual class. It's just because X is proper, not proper, we cannot use this class to define invariants. But then now first it can be embedded as U. And also, moreover, they assume that they want to extend this U. This is smooth. And moreover, the evaluation map extends. Oh, sorry, I think there's a typo. So evaluation map I from X extend to U. And then so far, all this construction still does not depend on W. So now the W, the superpotential restrict to each kinetic component of the inertia stack, which is a closed substack of our GIT quotient stack. And so then define W to be the pullback. And then this superpotential now on this U restrict to 0 on X. Our original restrict to 0 on our original moduli space, and this is enlarged to some U which is smooth. And they constructed a virtual fundamental class in here. So it's so there's some okay, so this is very technical, but fortunately, like today, we are going to use it in very simple example where this is much easier to understand. So then they use this to define GLSM invariants. Okay, so now we will now specialize to the very nice case. So first, now from now on, G becomes torus, and we consider genus 0. So in orbifold quasi-maps theory, the I function is obtained by C-star localization on stacky loop spaces, which is the orbifold version of given Tau's toric map spaces, which arose in the proof of mirror theorem for toric complete intersections, or toric varieties themselves. So we will introduce LG Landau-Ginzburg loop spaces, which are very similar. So the domain is just, so it will be like fixed domain, and it's just a teardrop. And so Mark Shoemaker has some other definition of I function using like with 2 mark points. So it will be convenient because we want to allow different A's. So we know that the O1 on PA1 is like degree 1 over A, right? So it will be convenient to introduce this notation. So given an effective class beta, so effective class beta, it's basically the degree of so the degree is now the degree of gamma bundle, but because the degree of gamma bundle can be split rationally into a degree of G bundle and the degree of the C star omega bundle. And C star omega bundle, the degree is fixed, right? So it's 2G minus 2 plus a number of mark points. So effective class just means that it can be realized by some Landau-Ginzburg map. So then we define, yeah, it's just the H0 and H1. Yeah, so basically in this case, this so this recall that now the domain is fixed and the bundle is fixed by the degree, and also this V is split into a direct sum of M plus kappa line bundles, and these will be their degrees, which can be rational. So for rational degree, then we introduce orbifold point at the infinity. So then the degree beta Landau-Ginzburg loop space is just a GIT quotient. So GX on the ith component with the character DI. So this is like some quantum version of the GIT quotient stack itself. And yeah, this is actually it's very nice because now this is the analog of, so this is actually a like smooth toric, the smooth toric the Landau-Ginzburg stack, and the obstruction bundle is a vector bundle. So and this defines a like perfect obstruction theory. And now seeing the like quasi-maps theory, or even earlier in like given Tau's work. So we are going to use localization. So C star Q rotate the P1 and T star X linearly. So we have this torus acting on a smooth Landau-Ginzburg stack, and this obstruction bundle is equivariant. And so now, but then here, if we do the whole thing like so for the whole thing, the mark point, which is the infinity, might go into the unstable locus. So yeah, so we consider the part which is an open substack such that evaluation map at infinity is defined. That means the infinity goes to the stable locus, then we have this. And then this is not proper, but then actually we consider the C star Q fixed locus. It actually becomes a closed substack of this particular connected component of the inertia stack. And moreover, we can compute, so the fixed locus, so the virtual normal bundle, which comes from this X beta and the obstruction bundle, it can be computed easily, and it has an extension to just the X zeta V. So now we fix this effective class, and just so now, like before, we have this very general thing, right? So now the boldface before is like some Landau-Ginzburg moduli space. In this case, this will just be F beta Z, and the superpotential. So the evaluation map now becomes inclusion. And also the superpotential, when you restrict it, when you pull it back to F, the superpotential becomes 0. And so it's already smooth, but we need to enlarge it so that the evaluation map is like, so the smallest, so recall that the evaluation map, when we extend to U, we want the evaluation map on U to be like a smooth map. So the smallest one we can take is just the whole X. So yeah, just apply this general construction to this very special case. And of course, this is just, I mean, before the quotient, this is just a linear subspace. So it's the zero locus of a regular section of T quadrant vector bundle, which is a direct sum of line bundles. And this section basically just corresponds to some coordinates. And then the superpotential can be, just written, just be factorized. And then we just consider the Kazoo factorization. So alpha is a section of a dual bundle or a cosection of BU. And so what is before, there's some definition in the narrow sector. So the narrow sector just means the superpotential restricted to, so V is a narrow sector if the superpotential restrict to, if chi CV is compact, and in such, so in that case, the superpotential restrict to 0, and then in that case, alpha will be 0, and this is just the Kazoo complex. So we apply to this Kazoo factorization, and we get this thing which is in the right space. And also, we can also consider another closely related theory, which is you take the same, you take the same VG C star R and the stability condition, but you change the superpotential to 0. So we know that there's this philosophy, which is if you have a regular matrix factorization, then it should be regular in the sense that, so this beta is a regular section, then we can think it as the deformation of like the case when the superpotential is 0. So then we set the superpotential to be 0, and recall that this doesn't change the moduli space at all, right? and it will just only change this the support of this class. And so let's consider so we define the GLSM I function of our original GLSM in this way, just using this F beta. And then when the superpotential is 0, then originally the T star, the big torus, T tilde is the big diagonal torus on GLV. So this doesn't act on, this doesn't leave the superpotential invariant, but when the superpotential is 0, the whole theory has this bigger torus action. And of course, when the superpotential is 0, then Z is equal to the whole thing. So the support is still non-compact. But now when the superpotential is 0, we can use T tilde equivariant localization and define T equivariant I function. And this T equivariant I function has a non-equivariant limit. And moreover, when in this case, we can actually just change the R charges, like C star R action to make it 0. And if we let the C star, if we formally let the R charges, which is like weight of the C star action to 0, we actually get the I function of like a case without superpotential. Okay, so these are the definition of I functions. And now we also have 2 definitions of central charges. So in GLSM, so the D brane is a matrix factorization. So this will only depend on the K theory class. So we take the I function. So now we assume, like in this case, we assume the critical locus is critical locus of superpotential curly X is proper. So this pairing is well defined. So gamma hat is some analog of Irritani's gamma class, and this Chang character has like contribution from different twisted sectors. Similarly, so now we consider the superpotential is 0, and we consider T equivariant, T tilde equivariant theory. So then we can use the T tilde equivariant Poincare pairing. Okay, so in many cases, so at least for me, the T equivariant thing, for me it's easier to compute because you can localize and you get contribution from fixed point. And the good news is there are in some cases, like the T equivariant central charge has a non-equivariant limit. In many cases, this GLSM central charge can be obtained as a non-equivariant limit. So now let's focus on this is so what we will do next is this is the this is the Higgs branch. So now in the Coulomb branch, so this is in 2013. So this is before any of this GLSM invariants were defined, right? Even before the like fun job is run. In this paper, I think we consider Abelian GLSM. So G is a torus, and also Calabi-Yau condition, so that there will be better convergence properties. So now we consider a complexified or stringy Kähler class, whose real part is C, and imaginary part is this B field. And now we want to, so this alpha will be like it will almost correspond to the equivariant perturbation. So given any T equivariant K-theory class on the stack, we define this hemisphere partition function as follows. So if alpha I are all 0, oh yeah, so maybe I'll first say this. So basically the contour is like you shift the purely imaginary. So it's a so we consider some contour integral on the Lie algebra on the gauge group. So it's a complex kappa dimensional space, and the contour is like you take the purely imaginary. So if you under the exponential map, this will be mapped to like the compact maximal compact subgroup, but you shift it by delta, and the delta and di and alpha I should satisfy these properties. And then basically, if you are given any like b, and then the integral is defined in this way. So this is a multi-dimensional Mellin transform of gamma. So this gamma is very much related to the gamma class, and this is very much related to Chen class. And also, if you let alpha to be qi over 2, where qi are the R charges, so you get a so this is the GLSM invariant defined in the Coulomb branch. So this is what we mean by Coulomb branch. So proposition is the following. So now we can take LT. So this is some. So so maybe so you see that if we consider like T tilde equivariant bundle on this quotient, it's given by a character of T tilde times G. So this LT is like the T tilde X trivially and GX by some G character T.
When you say you consider this the Coulomb, what is this?
Oh, sorry?
You're saying you consider this the Coulomb. I don't get what is this. If you wrote down a couple of data, but what is the Coulomb?
Oh,
some kind of questions.
So the thing is, the way I think about it is, it's like you are given the same data, given the GLSM VGC star W theta, and then using the same data, and you are given. So recall that. So say I give you some T equivariant. T equivariant K-series class. Now it's on the whole stack. Then there's a way to define this, and this actually in each phase will have a power series expansion. And the Higgs-Coulomb correspondence says this power series expansion will coincide with this central charge defined using like GLS. Defined using like by pairing with the T tilde equivariant I function. That's the.
And where's your power series or your?
Oh yeah, so this is the first we so let's just study line bundle, since everything can be written as a combination of some line bundle. So if you fix a line bundle, then this has some convergent. It's analytic on this. So there's a so the condition, there's no condition on the Kähler, but there's some condition on B, and this depends on which line bundle. Okay, and more precise. Yeah, there's some. But then that's just some proposition. And okay, sorry, this is so this is probably so let me just give you the idea. So the idea is now you take so say in the one-dimensional case it's just C, right? And then this is what happened in the quintic example. So you have some integral, and you integrate like imagine it's a purely imaginary part and shifted purely imaginary part. And then if you want to get a group of this central charge in the Clavial geometric phase, you close the contour on the positive on one direction. And if you want to get FJR double close on the other direction. So these are power, so you have power series expansion. Yeah, but so I think when I first start to work, it's like we say, let's do the mirror quintic, and then there's 101 Kähler parameter. So I see my Konstantin Aleshkin, he will start to take this 101 dimensional contour and start to deform it and inductively and get infinitely many 101 dimensional torus. And then each you compute. Because this is the way, if you do the equivariant perturbation, then it's easier. You don't have higher order poles. So this is just by deforming it. So on each phase, so you deform it, but as you can see, if it's any dimension, and when you deform, then it's more complicated. But in any case, on each phase, there's some region where it converges absolutely and uniformly. And there's some condition on zeta. Zeta is in some shifted Kähler-Coulomb, then we have this power series expansion. And the Higgs-Coulomb correspondence says, under some easy change of variables. So the right-hand side is the central charge defined in terms of the T tilde equivariant I function. And left-hand side is the expansion of this hemisphere partition function in certain phase. So that's the idea. And this has been proposed by physicists. So the proof is by careful manipulation of coupled dimensional cycles and convergence checks. Check the integral converges, and each integral converges, but then you have a power series, you have an infinite series where each series is an integral, so series also converges. And so we need a Calabi-Yau condition. So when we define the Higgs range, there's no Calabi-Yau conditions needed. But here Calabi-Yau condition will give us better convergence properties. Okay, so finally wall crossing. So for abelian GLSM without superpotential, so Borisov-Hodja did the Calabi-Yau non-equivariant case, and Coase, Iritani, John, they did the Calabi-Yau case, but still Tori case equivariant, full equivariant, and it's a Kreppen transformation. So we consider, basically now you consider two adjacent chambers in the stability conditions or two top dimensional cones in the secondary fan, right? So, and then they intersect in some wall, and the wall is, so the wall is defined by some edge, which is co-character. So this is, these are some notations, but let's just look at, so the thing is, it's, okay, so if T satisfy the great restriction rule, then there is a, so then in the positive and negative chamber, so in C plus and C minus, we have this expansion. So basically there are so the non-essential, so because on the two sides of the wall you have different so let's just think in this way. You have some torus fixed. So basically when you So you can write this sum of fixed point, and on one side of the, so if each fixed point correspond to some minimal anti-clone, and if it's not changed under this, if it's not touched under this toric Krappan transformation, then it's non-essential, and you get a series which converges on both sides. And the essential, so then the essential part is a one-dimensional integral, and you close contour in different ways. You get the you get a central charge in plus and minus, C plus and C minus. Okay, so this great restriction rule. So thanks to many work like including Bella, Ferraro, Kazakov, helping listener. So if you open their paper, it's in much greater generality. But if we read the rule in this particular case, then we see that this is exactly, the convergence is exactly the great restriction rule. So in particular, this implies the following. So under this, so the great restriction rule gives you an equivalence of a derived category on the plus side and the minus side. So if you take a brane and satisfy the great, so if you take a brane and you compute the central charge on the plus side, and then you consider the central charge of this image under the great restriction map, which is equal to Freer-Mukai in the toric case, they are related by analytic continuation. So recall that like early in this talk, there is this symplectic transform between I plus and I minus, and it can be described nicely in this way. So
this is like going to the window.
Yeah, this is a window, and so you specify, in this case you specify the length of the window, right? But then there's so where the window is depend on the B field.
So you can pick additional exceptional.
Yeah. Now it's right. So right, very good. So that we should next step is a describant transformation, right? Yeah, thank you. And also we should do general G. Yeah, thank you for your attention.